Hello everybody, this is Shadid Qasas, Sharjah American International School, and today we're going to revise Chapter 3 for Grade 10. Chapter 3 basically discusses the two-dimensional motion, and I mean by two-dimensional motion, motion in two dimensions or two directions. Like a projectile motion, when you throw an object, basically that follows a two-dimensional motion. When there is an airplane that takes off or landing, this is a two-dimensional motion because you have x and y at the same time. You're moving in two dimensions, two directions. In order to understand the two-dimensional motion, you need to be able to add vectors, subtract vectors. You need to identify the properties of vectors. So first of all, we need to define what is a vector. The vector basically is any physical quantity that needs a magnitude and a direction. The magnitude is identified by the length of the vector, and the direction is identified by the direction of the vector itself. So if I have a force like that, and a force like that, I know that this is F1 and this is F2. I know that F2 is more than F1. They have the same direction, but it is more in magnitude. But if I have something like that, so F2 is equal to F1 in magnitude, but opposite the direction. So if this is a positive F, this is a negative F1. Okay? In order to add vectors, you have two basic ways. You have the graphical method, and you have the algebraic method. The graphical method, you need your ruler and your protractor. I call it translation problem. You need just to translate the problem into ruler and protractor. So suppose that I'm moving with 200 meters to the east. So I will use 20 or 2. Let's say you're moving 20 meters to the east. So with your ruler, you will draw 2 centimeters. So suppose that I'm using higher scale. With your ruler, I need exact measurements. So this is, for example, let's say that it is 150 kilometers. For sure, you cannot draw 150 centimeters on the board. So you need 15. You can draw 15 with your ruler. So this will be 15. Let's make it a little longer. You need to use your ruler to draw that. So this is 150 meters. 150 meters to the east, which is in your scale, that is 15 centimeters. And then the airplane flies at an angle of 30 from the horizontal with 140 meters. So it traveled 140 meters, 140 meters at an angle of 30. So let's adjust the angle. So you need to start from here, put your protractor here. He said from the horizontal, so I need to count the angle from this side. So 0, 10, 20, 30, put a small point here. And then with your ruler, 14 centimeters. And here we go. So this is 140 meters, which is in your scale, it is 14 centimeters. And then draw your problem. Draw the resultant. The resultant is here. With your ruler, draw it with a dotted line like that. Now I need the resultant and the resultant magnitude and the resultant direction. The magnitude, you will get it by the ruler. So put your ruler on the resultant, identify how much is it. So suppose that it is an 18 centimeters. So it is 180. Don't forget the scale that we have used. And the direction is this theta, or the angle. This theta, basically, you will identify it from the very beginning. So here, put your protractor and count. 0, 10, 20, 30, it will be about 25 or something. 25. Unfortunately, this method is not that accurate. That's why we needed to use the algebraic method. In the algebraic method, you use Pythagorean theorem and the functions, the 4 functions. Pythagorean theorem is telling you that if you have a right triangle, like that, this is A, this is B, and this is C, this is theta. So he says that a squared plus b squared is equal to c squared. C is the hypotenuse, a is the adjacent, and b is the opposite. It's opposite to the angle, that's why it's an opposite. You can just remove the square here and put the square root. So c is equal to a squared plus b squared, which is equal to c, okay, under the square root. This is Pythagorean theorem. And then the functions, you have three functions, and they are so, ka, tua. Sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tan theta is equal to opposite over adjacent. These are the three functions, and you can just memorize them by memorizing SO, K2A, SOH, CAH, TOA. Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tan is equal to adjacent over, opposite over adjacent. That's fine. So this is Pythagorean theorem, and those are the functions. You are using them to find the resultant magnitude and direction. So what kind of problems that you may face in this spot? You have three basic categories. The first category, so let's identify the categories here. The first category in the algebraic method is when you have two components and you need the resultant. Suppose that a certain object is moving to the east at 50 meters per second. You don't need any rulers or protractors here because you are just drawing scale. You don't need any measurements here. Okay? You're drawing this with your hands without any measurements. So to the east 50, and then to the north with 40 meters per second. Find the magnitude and direction of the resultant. This is my resultant, R. I need the magnitude, which is the length, and the direction, which is the theta. So I will find it using Pythagorean theorem, which is a squared plus b squared is equal to c squared. Remove the square root. So 50 squared plus 40 squared. I need someone to calculate, please, the values here. Under the square root, which is equal to, this would be the resultant, and you use Pythagorean theorem because you have the two opposite and adjacent. You have those two arms. Without those arms, you cannot identify or you cannot use the Pythagorean theorem. So how much is that? Huh?
64.
64. 64, and you have to use the same unit, meters per second. I need the direction. Don't forget that you need the magnitude and direction. This is the magnitude. I need the direction theta. For sure, I'm not going to use my protractor because this is the algebraic method. We don't use any exact measurements. So you need to use the functions. Functions are SO, K2A, sine, cosine, and tan. What is the best one that can be used here? The tangent, because we have already 40 and 50, which are the opposite and adjacent. So you say that tan opposite minus 1, tan minus 1, or tan inverse is equal to, theta is equal to tan minus 1 opposite 40 over 50. So the theta is 39 degrees. So this one is 39 degrees. This is case 1. Case 2 is the opposite. I will give you this and the angle, and I need the two components. So let's plot it here. This is case 1. Case 2. Case 2 basically is telling me that if I have an airplane that moves at 10 meters per second at an angle of 30 degrees. This is a two-dimensional motion. This means that I need two components. And the two components are the x and y. So I need to draw my right triangle, right? So this is my x, and this is my y. This is component 1 and this is component 2. As you can see, we cannot use Pythagorean theorem because I have two unknown values. I cannot use Pythagorean. So I need to use one of the Huh? Sine, cosine, and tan. We call it functions. We need to use one of the functions. So in order to get the x, I will use x, which is the adjacent, cosine. So and the y? Sine. Sine. So in order to get the adjacent, I will use the sine, the cosine, and for the y, which is the opposite, I will use the sine. How are you going to do that? So you know that cosine 30 is equal to adjacent over hypotenuse, which means x over 10. By the cross multiplication, you will find that x is equal to 10 cosine 30, which is 9. Use the same unit meters per second. The same for the y. Sine 30 is equal to y over 10, which is equal to y is equal to 10 sine 30, which is 5 meters per second. So now I found x and I found y, and that's it. This is your question. Find the two components. Find x and find y. So this means that this airplane that is flying or taking off at a 10 meters per second, let's consider it as a toy plane because 10 meters per second is very long. So this means that at an angle of 30, this means that the running velocity or the speed on the runway is x, which is 9 meters per second. And it flies upward at 5 meters per second. This is the meaning of the two-dimensional motion. This is the meaning of adjacent and opposite. This is the meaning of two components. You got the two components. You got the horizontal velocity and vertical velocity. The third part is to add vectors that are not perpendicular. Basically, this is the x I'm going to use. This is one of the questions. Why I used the cosine for x? Because the only thing I can use in the functions, look at the functions again, it is so, tan, 2. The x is an adjacent or an opposite here. It's an adjacent because it touches the angle from one side, right? So I have two functions that have that they mentioned the adjacent. I have this one and I have this one, right? Let's try this one. Tan theta is equal to opposite over adjacent. But you don't have the opposite. You need the adjacent, right? You don't have the opposite. The opposite is y. I didn't get it yet. So the only function that works here is the CAH, the CAH, which is cosine is equal to adjacent over hypotenuse. Because the adjacent is unknown, but the hypotenuse is known, so I can use it, right? Did I answer your question? Very good. So let's move to adding vectors that are not perpendicular. And in order to add vectors that are not perpendicular, we need to use my secret. So whatever the problem is telling you, so suppose that let's have very complicated problem, like an airplane moves at 10 meters per second to the east, and then at 30 degrees from the horizontal, it moved 5 meters per second, and then to the north with 2 meters per second. And then at an angle of 40 degrees from the horizontal. 40 degrees. It moved 3 meters per second. This is a very complicated problem. How can I find the resultant, which is this big line here? This one. Let's make it dotted. How can I find this big resultant using Pythagorean theorem and function? This type of problems is called adding vectors that are not perpendicular. And we have a secret for that. Make any inclined line as hypotenuse in the right triangle. Very good. So I need how many inclined lines in this problem? Let's count. 1, 2, and 3. And I mean by inclined line, an inclined line that has a theta, that has an angle. So let's start with this one. Let's draw the angle here, the triangle. 1 and 2. So I have x and y. And because I'm having different angles, different triangles, so I will call this 1 and 1. Okay? This one, can you find x1 and y1? Using the second type of problems? So let's find them. Yalla. x1 is equal to, right away, 5 cosine 30, which is equal to 4 meters per second. Y1 is equal to 5 sine 30, which is 2.5 meters per second. So I found this piece, which is 4, and I found this piece, which is 2.5. Very good. Where is the second inclined line? This one. Can I make a right triangle? Right triangle, so go there and there. So this is x2 and y2. Can you find x and y using the same way? Yes, x2 is equal to 3 cosine. It's 40 basically. Triple 40. Doesn't appear so. 3 cosine 40, how much is that? 2 meters per second. Y2 is equal to 3 sine 40, how much is it? 2 meters. Are you sure? No, it can't be. This is not 45.
1.9.
Huh? 1? Oh, okay. 1.9 meters per second. Very good. So I found this small x and this one. So there is a third line that I need. There is a third resultant, which is this big one, correct? Okay. So what should I do now? Yes? Very good. I need to connect this part and I need to connect this part. So connect this and connect this. Now look carefully at the pieces of the big right triangle. This is the big right triangle. Right? Which is this one. Right? This adjacent, so this is my result and I need the direction. This big adjacent is made of 10 plus x1 that you got from the first one, and this part, x2. It is parallel, right? Okay, what about this big one? What are the pieces? Y2, and this part? This is this vector, right? 2. So it is y2 plus 2 plus y1. Very good. y1. Can you find this? Can you find this? Okay. And then use your Pythagorean theorem telling you that a squared plus b squared is equal to c, so square root, and find the angle tan minus 1. Opposite over adjacent, and that's it. This is how to add vectors that are not perpendicular. Whatever the complications, you just use my secret. Make any inclined line as hypotenuse in a right triangle. Amazing. Okay? So let's move to the projectile motion. And the projectile, should I erase this? Okay, you have it already, so let's erase this. Okay, so what if it's very good. Anyway, so how can I use the projectile motion? How can I solve problems with projectile motion? First of all, you need to identify what type of projectile motion is that. You have two main types of projectile motion. You have a projectile that, very good, it is launched horizontally, and you have a projectile motion that is launched at an angle, theta. This one looks like that. I call it rolling falling model. If you have something rolling or moving with a certain VIX, and you just have a VIX here, because the object is moving horizontally, then it will fall down like that, making a projectile. This part is called X, or we call it, let's call it delta X, which is the range. How far it fell down from the edge of the bridge. Edge of the bridge, it's nice, right? Edge of the bridge. You have the height, delta Y, and delta Y is always a negative value, if the object is falling for sure. So, and you have the acceleration, which is negative 9.8 meters per second squared. Delta Y. You have here VFY, which is the final velocity before striking. All of these values are the values of the physical quantities in a projectile motion. The range, which is the horizontal displacement, the height, which is the height of the bridge, and you have the VIX, which is the initial horizontal velocity, and you have the VFY, which is the speed before striking the floor or the ground, okay? Which is the crash speed, basically. What are the formulas? Let's do it. How many formulas I have to use? Two types, horizontal and vertical. The horizontal is delta x is equal to VIX delta T. Amazing. So if I needed delta x or the range, I just need to know the VIX and the time. Very good. For the vertical, I have two equations. I have one related to the delta y, which is delta y is equal to half negative 9.8 delta t squared. Amazing. I have something else, which is VFY squared is equal to 2 negative 9.8 delta y. So those are the two equations I'm using here in the projectile launch horizontally and launch horizontally. So I have delta x, delta y, and VFY squared. Let's talk about this part. This part basically looks like that. So this is the range delta x. You have different delta y's here. At the maximum point, you have delta y maximum. And we said that this is a very specific case because in this part, your VIX is equal to VI because it is horizontal, right? And your VIY, which is VI sine theta, is equal to 0, right? Right? So VI sine theta is equal to 0. What are the equations? Let's compare the equations. So delta x was VIX delta t, but here delta x is equal to VI delta x is equal to the VIX became VI. VIX became VIY. VI cosine theta delta t. This is the delta x. The delta y is equal to. I need to keep this part, but there is a new part added because there is an angle here. So it is VI sine theta delta t plus half negative 9.8 delta t squared. Amazing. Very good. So I just added this part. VI sine theta delta t. And it has the same second part. Half negative 9.8 delta t squared. VFY squared. VFY squared. It is VI sine theta squared plus 2 negative 9.8 delta y. Amazing. And those are the two equations for the projectile launch at an angle. So if you compare, you'll find out that this is delta x, VIX delta t. This is VI cosine theta delta t. This one delta y is equal to half negative 9.8 delta t squared. I've just added this part, VI sine theta delta t, because of I have now two components for the V. Here, the VI had one component, which was VIX only. I didn't have any VIY. But here I have a VIX and a VIY. I have a component here, I have a component there. This one is a VI sine theta, cosine theta, and this one is a VI sine theta. I need to use it. Okay? This was a revision for chapter 3. Thank you very much.